everybody. Today we're going to look a little bit more at gravity. What we're going to be doing is looking at the relationship between mass and weight and why the acceleration due to gravity at any given location does not depend on the mass of the object in free fall. Okay, so let's start with this. First, what I'm about to show you, you are required to be able to derive. You'd better be able to show this on paper on a test. No ifs, no ands, no buts, no maybes about it, okay? You've got to be able to do this. So let's take a look. For any given mass, M, okay? We'll say M sub O, all right? Then let's look at the two ways we can find the gravity of the mass here on Earth. The first way is the short way. We can find the gravity on Earth, and capital E stands for Earth, by taking the mass of the object and multiplying by the acceleration due to gravity when it's in free fall on Earth. Okay? We can also, according to Newton's universal law of gravity, we can find the gravity between the mass and Earth this way. We can say big G times the mass of our object, whoops, my pen seems to be running out of ink, times the mass of Earth divided by the radial distance of Earth squared. That would be basically the distance between the object and the Earth and their centers. Now, both of these are valid ways of finding the gravity acting on an object on Earth. So these basically are the same. You'll get the same answer. So if that's the case, then why don't we take this expression for the gravity and this expression for the gravity? Oops.
Mr. Delaney, please dial
I just love it when they interrupt me. Okay, so as I was saying, let's set the two expressions equal to each other. So here we go. We've got the mass of the object times its acceleration in free fall on Earth must be the same as big G times the mass of the object times the mass of Earth divided by the radius of Earth squared. Now, let's look at that for a moment. Algebraically, what would your algebra teacher say? Look at both sides. What do you notice? Oh, well, the mass of the object is in the numerator on both sides. That means if we divide both sides by M sub O, it cancels out. What does that leave us with? That leaves us with G sub E on this side equals, and look, I'm running out of ink in this stupid pen, big G times the mass of the Earth over the radius of Earth squared. Ugh, boy, let me tell you, it's running out. Okay, what does this say? What is this telling us? This is telling us that the acceleration due to gravity on Earth depends only on the mass of Earth itself and the radius of the planet. Notice nowhere in here do we have the mass of the object because the mass of the object canceled out of the equation. So the acceleration due to gravity on any planet, the acceleration due to gravity on any planet equals big G times the mass of the planet that you're on divided by the radius of the planet squared. Has nothing to do with the mass of the object in free fall at all. Isn't that just freaky? So this is why if we went out to the balcony and dropped a bowling ball and a golf ball off the balcony, they'll hit the ground at the same time if we drop them from the same height. That's because the mass of the bowling ball and the mass of the golf ball have nothing to do with their accelerations in free fall. Only the mass of Earth and the radius of Earth has anything to do with their accelerations. So they have the same acceleration. They will hit the ground at the same time if released from the same height. How about that? Okay. So let's wrap it up right here. All right. G never depends on the mass of the object in free fall. Okay? All right, now, another situation we need to look at, because this pops up quite often on the AP exam. And that's because, unfortunately, not all surfaces are completely horizontal. Many surfaces are inclined. So once again, we have to think about what's going on an incline. Now, back when we were looking at linear kinematics, we learned how to resolve acceleration due to gravity on an incline to see how much of the acceleration due to gravity an object would have along the incline. Now, it won't be in free fall if it's accelerating along the incline because it's not falling straight down. It's not just gravity that's acting on it. The surface of the incline also acts on it. So, we're going to look today at not the acceleration, but the forces in this case. Now, we already understand about the accelerations, but what about the forces? So let's take a look, all right? Let's suppose that we have an object on an incline. Okay, I'm just going to put a dot there to represent the object. Doesn't matter what the object is. Now, we know that gravity is pulling straight down to the bottom of the page. All right, and here's how we would find it here on Earth, mg. Okay, I'm not going to even say F sub g. I'm just going to say mg. And it is perfectly okay on the AP exam to label it thusly. Okay, you can put FG if you want. You can also put a capital W for weight. Same difference. I tend to use mg, and you'll see why in a moment. Now, this particular force always pulls straight down to the bottom of the paper, but notice the object is not falling. That's because there are other forces acting on the object. Mainly, there is the normal force from the surface, which pushes back up that way, okay? Then sometimes there's also friction, with which if the object is moving down the incline, it points up the incline. If the object's moving up the incline, the friction points down the incline. All right? I'm not really all that interested in those particular forces right now. I just want to look at the weight itself. So what we need to be able to do is take the weight and resolve it into pieces that are also perpendicular and parallel to the incline, like the other forces that could be acting on the object. Because if we have one force that's sticking out at a weird angle, then we have to do a lot more math. We have to do vector addition using resolution, and that is a lot more complicated, as you remember. So what we're going to do is take the weight and break it down into components. One component will be parallel to the incline. The other will be perpendicular to the incline, just like any other forces that are acting on our object. All right, so here's what we do. I'm going to start with the horizontal component. Let's go with the vertical component first. I like that one. So what we're going to do is we're going to draw a line between the tip of the weight vector and the axis and the incline such that it is perpendicular to the incline. So I'm going to go back like this. That looks pretty perpendicular, don't you think? The tip would be right here because we're going to pretend this is a resultant. And resultants are always tip to tip and then tail to tail. So where's the other vector? All right, the other vector would be this one right here. I drew it just a little above the incline line so you could see it. So now, Here is a component of mg that is parallel to the incline. Here is a component that is perpendicular to the incline. They create a right triangle with the weight itself as the hypotenuse, just like we want. All right, how do we find these two components? Well, guys, it's pretty much the same thing we did when we were talking about the accelerations. The only difference is now we have an m. Multiplying m times the acceleration gives us force. So let's look. If you know the angle of the incline, then just like before, since this is the hypotenuse and this is the longest leg, it's going to be the same over here. Here is that angle right there. And yes, we can show through a proof, although we're not required to, thank goodness. We could show that we get two similar triangles right here, and these two angles would be congruent. Knowing that, now we can write a formula for each of these legs. The leg that is parallel to the incline is also opposite the given angle. So that means we would say hypotenuse times the sine of the angle, because we always use sine for the opposite leg. Hypotenuse times the sine of the angle. Now remember, when we did accelerations only, it was just g sine theta. But now to make it force, we multiply by m. All right, now the other leg, perpendicular to the incline, is adjacent to the given angle. And we always use the cosine for the adjacent leg, so we get mg cosine theta. And remember, when we did just the accelerations, we had g cosine theta. Now to show the force, the component of the weight, instead of just an acceleration, we put the m there, mg cosine theta. Okay? Now, what would happen if the incline were slanted the other way? Well, you just get the mirror image of what we have here. So real quickly, I'm going to draw it so you have both of them to look at. All right, if this dot represents our object, then we're going to draw the gravity straight down and label it. Okay, then we're going to draw a component that is perpendicular to the incline between these two. Got to be perpendicular to the incline. Don't make it out over here somewhere. That gives you an acute angle. You want a right angle right there. 90 degrees, like a box. Okay? So there's mg cosine theta, because our angle would be right here. All right? And then the one that's parallel would be right here. And that would be mg sine theta. Ooh, look, maybe that'll help a little bit. All right, there we go, mg sine theta. Now that's not so bad, is it? No, not bad at all. All right, now let's take a look at this example. You're going to need your calculator, and if you've got your calculator, please first go in and check your mode. Make sure that you are in degrees and not radians. You want degrees, okay? Because we're going to be using sine and cosine. We want to take the sine and cosine of degrees of arc, not radians. All right, so this says a 100 kilogram crate is sliding down a smooth ramp. Determine the component of the weight which causes this to happen. Well, let's take a look. If we want the weight to help the object slide down the ramp, we have to use the component that's in that direction, and it would not be this one. This is not down the ramp, it's perpendicular to the ramp. So that means we want this component because it points along the ramp. This component of the gravity is always the component that makes water flow downhill, makes balls roll downhill. If you have your car and you forget to put your parking brake on and your regular brake fails, it'll roll downhill because of this component. Okay, so this is the natural tendency of all objects to slide or roll down inclines, okay? So this is the one they're asking for. Well, let's determine that. All right, so I'm going to use the green one because the blue one's almost out of ink. So we want to find out what is mg sine theta, okay? All right, so that would be 100 kilograms times 9.8 meters per second squared, and it just dawned on me I didn't type in an angle for this, so let's just pick one. I think I used 25 degrees last year. All right, so we'll use 25 degrees there. It's not a big angle. Actually, it looks like it might be more 10, but in this case, we'll say 25. Sine 25 degrees. Okay, so you get 980, and sine 25. If you stick that in your calculator properly, you should get 414 newtons exerted along the incline, down the incline, this way. And that's making the crate slide down the incline, okay? That's the amount of force doing it. Now, that wasn't so bad, was it? No. Now, when you look at your assignment for this, I want everybody to notice, and I'm going to show you right now so that you'll understand. This is the assignment you're going to be doing for this. And I want you to notice that each problem has two different inclines. Well, I mean, they're the same incline, but you're going to be drawing two, because I'm going to tell you, I want you to remember right now one of the things we said about free body diagrams. For a free body diagram, we never, ever draw components on a free body diagram. We only draw the actual forces acting on the object. So on the AP exam, if they want you to draw a free body diagram, you better only have the actual forces acting on the object. You better have no components on it at all, or you lose points, okay? Because they want what they want, no more, no less. That's why I have two inclines here. The first incline is going to be for the free body diagram, okay? The diagram that you're actually going to draw with the real forces acting on the box. Then the second diagram is going to be the component diagram, the components of the weight, okay? So that you get practice drawing them. So look at this first one. I'm going to do it real quick. We have a 50 kilogram box at rest on the surface of an incline. Now, why is it not sliding down? Well, apparently there's enough static friction to prevent the component of the gravity that points down the incline from overcoming the inertia and pushing it down the incline. So the friction's just too big. So it's at rest. So let's draw the free body diagram. First, we know gravity acts on the object, so there it is. Secondly, we know that it's on a surface, and surfaces push perpendicular to themselves. This if it's pushing down on the incline is pushing back perpendicular to itself, just like this. We call that a normal force. Remember our free body diagram assignment we did? There it is. Okay? And then lastly, the reason it's not sliding down but at rest is because there must be some friction. So I'm going to draw a little friction vector right here. Now at the moment, we don't need to worry about static and kinetic. We'll worry about that, just friction right now. And that's fine, okay? Friction. So this is the free body diagram. These are the forces actually acting on the box to maintain equilibrium. Remember, it's at rest, so it's in equilibrium. That means the force is all balanced. How do we know? Oh, because this weight is made up of two components, and those two components are balancing these two forces. Aha! That's how we can figure out what some of the things are. All right, so let's look. If I redraw the weight right here, I know I put that on the wrong side. Hang on. I want to put it on the other side. Give myself some room. There we go. one component is perpendicular to the incline. See, right there, perpendicular. And that's going to be mg cosine theta because it's adjacent to the angle. And this component right here points down the incline. That's going to be mg sine theta. Now, if this box is in a state of equilibrium, it's because, look what we have. Remember, once you break something apart, you don't have the whole anymore, you just have the pieces. So now that we have the pieces, you can see mg sine theta will balance the friction, mg cosine theta will balance the normal force, the net force is 0, so the box stays at rest. Now, isn't that kind of cool? I think so anyway. All right? So that's what I want you to do with these. Now, the only other thing you have to do on this particular problem is I want you to find the value of those two components, which is why I gave you the mass and the angle of incline. So over here in the side, or maybe one here and one here, we could do mg cosine theta here. So this would be 50 kilograms times 9.8 meters per second squared times the cosine of 25 degrees, and you're going to get a value of, well, let's stick it in and see. I'm going to say 50 times 9.8 cosine 25, and we get 444. So we get 444 newtons for this component. Now this component over here, mg sine theta, is going to be 50 times 9.8. Oh, look at that. Meters per second squared. I give up. Here we go, meters per second squared. And in this case, it's going to be sine 25 degrees. And if we stick that into the calculator, 50 times 9.8, sine 25. Oh, look, and double check me on this, but I think I'm right. 207, is that 287 or 2? That's 207. 207 newtons of force down the incline, okay? So if this were an actual problem, and notice the object is in a state of equilibrium, and they said, what's the friction force? Well, you know, because it's in equilibrium, the friction is being balanced by this component. And you just saw this component is 207 newtons, so guess what? The friction must also be 207 newtons. It just points up the incline instead of down, okay? Because it's preventing the box from sliding down. If they asked you for the normal force, you'd think, oh, okay, well, we're in equilibrium, so the normal force is being balanced by mg cosine theta. Since mg cosine theta is 444 newtons, so is the normal force. They balance to 0. Isn't that cool? Okay, so that's what I want you to do on all of these. I want you to do a free body diagram. I want you to practice drawing the components of the weight and then find those component values. All right? Now, on the back, there's another item to do, and I'll let you read the instructions and go through that. You're going to go back through the diagrams, and you're going to look at each of these things for each diagram. On some of them, there may be answers. On some of them, there may not be. If there is no answer, if it doesn't pertain to that particular situation, then just put N/A, not applicable, something like that, okay? All right, you guys have a good time. We'll see you soon. Bye-bye.